Okay, guys, so now we're talking about specific heat, all right? So some things are going to heat up and cool down faster than others. So, like for example, our beach here, right? The sand, which has a low specific heat, is going to heat up a lot faster than the water that's out in the ocean, right? So water has a really high specific heat. All right, so let's look at some other things, right? Specific heat is just the amount of heat required to raise the temperature of 1 kilogram of material by 1 degree Celsius or Kelvin. So, for example, water, 4,184 joules per kilogram. So it takes a lot of energy, a lot of joules to raise up 1 kilogram of water 1 degree Celsius. So again, think back to our pool example, right? During the summer, your pool is going to be a lot cooler in the afternoon. Even though that sun's been shining, it doesn't heat up as fast. But when the sun goes down, you think about it, oh, my pool is still kind of warm from the afternoon sun, even when the temperature has dropped because the sun's gone down. All right, some other things like sand, right? There you go. The sand much lower, almost 664, so it's going to heat up a lot faster, but it's also going to cool down a lot faster. So that's why land heats up quickly during the day and cools quickly at night, and why the water takes longer. Right? So if you ever go to the beach at night, right, or during the day the water is cooler. So which way is the wind blowing? Well, the wind's blowing out towards the ocean, right? Because that I'm sorry, no, towards land. The air is blowing in towards land because the land heats up quicker, so that cool air flows in to replace that warm air that's rising. Then at night, right, the water is still warm, so that air is rising. So then the air on the beach is cooler. It flows to take its place, so the wind blows out towards the water at night. Right. So next time you go to the beach, just see if you notice that. And there you go. That's the convection currents. All right. So here's some other examples of specific heat. Right. Which one's going to take longer? 50 grams of aluminum or 50 grams of copper? Well, if I look over here at my chart, it gives me my different specific heats. Right. So when I look at it, I go, okay, aluminum's specific heat is 0.22, and then copper's is 0.39, right, or 0.93. So you can look over here. Here's the specific heat. So aluminum has a higher specific heat, so it'll take longer to heat up. It will also take a lot longer to cool down. Right, so that's why copper, they use it in wiring just because it conducts that electricity a lot quicker. Right, so you can see there's my specific heat. Right, aluminum's a lot higher. All right, so why does water have such a high specific heat? Well, when I look at it, right, here's the shape of water. They form these bonds, right? They like to kind of connect to each other, right? So you notice there's a lot of space in between. And then here in the metal, not quite as much space. So that water molecule forms some really strong bonds. So it takes a lot more energy or heat energy to break them apart. Whereas metals kind of have weak bonds. It doesn't take as much energy, right? And so that's why once you heat metals up, you can shape them in the direction you want them to be shaped. Okay? Alright, so how do I calculate changes in thermal energy? Well, here's our formula. Q is equal to mc delta P, alright, over times delta T. Alright, so Q is my change in thermal energy, right? That's my heat, and that's always in joules. The M, that's the mass of the substance. So like earlier, we had 50 grams of aluminum and 50 grams of copper. The CP, right, or the PT here, sorry, is the change in temperature, right? So that's going to be my final temperature minus my initial. So whatever it ends up, I'm going to subtract that from what it was originally. The CP, that's the specific heat of a substance. So whatever that substance is, I'm going to look at its specific heat. If it's water, right, that 4,184, I'm going to use that. So just some quick little things. If I see that it's a negative Q, well, that means that it's probably exothermic, right? Some of that energy has been lost. All right, and if I see it's a positive Q, so my number ends up being positive, then I know that heat was gained. It was an endothermic reaction. So let's try a problem here. 32 gram silver spoon cools from 60 degrees Celsius to 20 degrees Celsius. So how much heat is lost by the spoon? All right, so it's a nice easy way to do this. Let's first write our givens over here in our little box with givens. Right, so my mass is 32. My initial temperature is 60. My final temperature is 20. All right, don't know what Q is, right? But I do know that it's silver. So if I look at my chart, I can find that its specific heat is 0.235 joules per kilograms of Celsius. All right, so let's start with our formula, right? Q is equal to mc delta T. So plug in the mass, plug in my final minus my initial. Alright, 20 minus 60, so negative 40. So I plug it all in. 32 times 0.235 for the specific heat minus 40, right? So times negative 40, and I end up with a negative 300.8 degrees or zero point 0.8 joules. So, right, again, if we remember, it's a negative number. So if it's negative, then that means that heat was lost. Okay, so it lost some of that heat energy, which makes sense because, well, what happened? The temperature dropped down. Okay, so it cooled off. So that makes sense. All right, there we go. All right, so another problem. How much heat is required to warm 230 grams of water from 12 degrees Celsius to 90 degrees Celsius? So take my givens, right? The mass is 230. I know my initial is 12. My final is 90 degrees. I don't know what Q is. That's what I'm trying to find. But I do know that it's water, so it's 4.184 joules per gram per degree Celsius. Okay, use my formula. All right, let's plug everything in. So final 90 minus my initial 12. So my temperature went up. So you can probably guess, hey, you know what? This is going to be a endothermic reaction. It's going to absorb some heat. All right, plug everything in. 230 times 4.184 times 78, and I end up with my Q being 78,061 joules. All right. Well, again, since it's a positive value, that means that it was an endothermic reaction. It absorbed heat. All right. So once you start to see that, you'll pick it out and go, oh, this is easy. I can tell just by looking at what the temperature is. You know, did the temperature, was the initial smaller than the final? Was the final smaller than the initial? And you'll get an idea. All right, one more try. So a piece of iron at a temperature of 145 degrees Celsius cools off to 45. But you can guess, hey, temperature's dropping. I bet you this is going to be a negative number. If the iron has a mass of 10 grams and a specific heat of 0.449, all right, how much heat's given up? So let's put it in our givens. So 10 grams, 145 initial, 45 final. Don't know Q, but I know that it is iron, so that's 0.449 joules. And we'll give you this chart, so don't worry, we'll have it in class. So plug everything in, all right. My temperature, change in temperature is negative 100. So again, we know it's giving off heat, so it's probably going to be exothermic. Plug everything in, 10 times 0.449 times negative 100. And there we go. I end up with negative 449 joules. So again, it's a negative number. I know that it is a exothermic reaction. All right, so we'll finish up this last little bit of notes in the next section.